Section 4.1 is extreme values of functions. So our definition, let f be a function with domain D, then f of c, that's our function value, is the absolute maximum value on D if and only if every f of x is less than f of c, and it's the absolute minimum if and only if every value of f of x is greater than or equal to f of c. So here's some examples. If f is continuous on a closed interval, then f has both a maximum value and a minimum on that interval. So here's a case where they are at interior points, your maximum and your minimum. A case where they're at the endpoints, max and min. This one has a maximum at an interior point, but a minimum is at an endpoint. And this one has a minimum at the interior and a maximum at an endpoint. So any combination is possible for minimums and maximums as long as f is continuous. So classifying as local or absolute, you all remember this, absolute minimum is the value that is a minimum for the entire function on the particular interval, in this case the interval from a to b. A local maximum and minimum are ones that are not the greatest max or the smallest min, but they are in between. We call them local because there's no greater value nearby. So if I took an interval close to this is a maximum for that smaller interval. Same holds true for a minimum. A local minimum is the smallest point in a smaller value, no smaller value for f nearby this particular point, f of e. So, local extreme values. Let C be an interior point on the domain. Then f of c is a local maximum. This is the definition of what we just saw. If and only if f of x is less than f of c for all x in some open interval containing c. Another way to say that is near c. Local minimum, the same. All the other function values are greater than that one for an interval close to c. The function has a local max or min at an endpoint if the appropriate inequality holds for all x in a half-open domain. So in other words, approaching c from a particular side. Local extreme values. If a function f has a local maximum value or local minimum at an interior point, and if f prime of x exists, then f prime of c is 0. So that's the case when we're looking at a particular min or max in a particular area. If this is a minimum, a local minimum, then f prime exists here and it is 0. And the same thing here, f prime would be 0. Now remember, that only happens if f prime exists. So I could have a local minimum or maximum. Here's a local maximum. F prime does not exist here, so I cannot say that f prime is 0. So, what does that mean? Critical points. A point in the interior of the domain at which f prime equals 0 or f prime does not exist is called a critical point of f. So, critical point. Stationary point. A point in the interior of the domain of a function f at which f prime equals 0 is called a stationary point. Now this does not have to be a max or a min. I could have a function like this, tangent or x cubed, something like that, where there is a place where my derivative goes from increasing to decreasing, where f prime is 0, and yet that's not a maximum or a minimum value, but it is a stationary point. But let's look at how we find absolute value. So we're going to find the absolute max and min of f of x equals 3x to the 2/3 on this interval. The first thing we have to do is find our critical values. So this one has no zeros, but it is undefined at x equals 0. So our only critical point value is that f of 0 is 0. Now remember, we also have to check our endpoints. So f of negative 1 is 3. F of 2 is approximately 4.762. So of these three values, what would be your absolute extrema? The absolute maximum is 4.762 and it occurs at x equals 2. The absolute minimum is 0, occurring at x equals 0. So let's do this one. Try this one on your own and see what you can do. Okay, hopefully you did some good work on this. Let's see. First of all, we know that f is defined for any place where 9 minus x squared is greater than 0. So the domain on the interval is negative 3 to 3. Since the domain has no endpoints. Now remember, if this were the square root of 9 minus x squared in a numerator, then the endpoints of negative 3 and 3 would be fine, because the square root can equal 0. But since it's in the denominator, the endpoints do not count. So all the extreme values must occur at critical points. So our critical points are any place where this is equal to 0. So we take the derivative, and we get this for our derivative. The only critical point is at x equals 0. So the only candidate for an extreme value is f of 0 equals 1/3. Now, why is our critical point at x equals 0? Remember, when you look at this function, square root function in a denominator, that's going to cause a cusp. So we go ahead and put in 0, denominator gets smaller, and then the function rises. So there's an absolute minimum at 0. The function has no maxima. We'll look at that a little bit closer together, and that's it.